Good morning, everybody. This is a sort of a dual video to the previous one about injective functions. So here we're going to be discussing surjective functions. So last time we talked about the distinction between functions, right? And the definition of a function being really a domain condition, whereas with injective functions, that's more of a codomain condition. So surjective functions are going to be more like the injective functions in that it's a codomain condition. So let's draw a picture so we can recall what surjective meant. So if you had a function going from, say, a set S to a set T, if you want to check surjectivity, you need to go to the codomain, so this would be the T, and you need to look at each of the dots. Now for injectivity, we had a guarantee, right, that there was exactly, or excuse me, at most one line going into each dot. For surjectivity, instead of it being at most, we want it to be at least. So for a surjective function, I know I need to have lines going into all the dots. If I didn't have, say, this bottom line, whoops, if I didn't have that bottom line, this I know for sure is not a surjective function, right? I could have as many as I want coming into these other ones. Doesn't matter. If one of these guys in the codomain is left out, doesn't have a line going into it, it's not surjective, right? Surjective means there's at least one going in. Now you can have more than one, right? So if I have one going into all of these, and then I have some more coming in, that's totally fine, right? I could have three of them coming into this one. It doesn't matter. As long as I have at least one going in to each dot, I have a surjective function. All right, so let's come back to the problem now. So we want to find two different surjective functions from S to T, where here the S's and T's, as in the previous video, are given by the sets 1, 2, 3, 4, and A, B, C, D. So let's draw a little picture. There's our T, A, B, C, D. And again, we just need to make sure something goes into each of these. So we're going to have something coming out. Okay, well, where maybe the A just came from 1. How about that? And the B came from 2. And the C came from 3, and the D came from 4. There we go. We just found a surjective function because every point in the codomain has an arrow going into it. Okay, but we want two different ones, so all right, let's draw another picture. So we're going to have our S on the left, 1, 2, 3, 4, and then we'll have our T on the right, A, B, C, D. Again, to be surjective, we know we're going to need an arrow going into each one of these. And we just don't want it to come straight across because that's the function we already had. So, okay, how about this? I'll take the A and have it come from the 2, and the B, that could swap and go from the 1. And we do the same thing from the 3 here and the 4. That's just the same thing. Okay, so we've just crossed two of the lines. That's a different function, and we found two different surjective functions. Okay, now we want to find a function from S to T that is not surjective. All right, well, let's draw our picture again. 1, 2, 3, 4. And we go from our T, A, B, C, D. All right, now to be not surjective, that means one of A, B, C, or D, one of the points in the codomain needs to be left out. So maybe I'll have things going into A, B, and C, but nothing is going to go into D. So let's see, where does A come from? Well, A, maybe it came from 1, and B came from 2, and C came from 3, right? Just to be systematic. Okay, if I stop here, though, it's not a function. Why not? Well, I check over on the left, and because that's the domain, right? Function is a domain condition. Everything on the left has to have an arrow coming out of it. Well, nothing is coming out of 4. So I'm going to need to draw something coming out of 4, and it can't go to D. Why? Because we're supposed to have a function which is not surjective. Something has to be left out. So this 4 better go somewhere else. Okay, well, easiest one, let's send it over to C. So there would be a function, right? Everything on the left goes to one thing, has one arrow coming out of it, but it's not a surjective function because on the right in the codomain, I'm missing a point. All right, there's a point that doesn't have an arrow going into it. Okay, final question. Explain why there is no surjective function from U to S. So U we haven't used yet. So let's say we wanted to have a surjective function from U, and U consists of the circle, the asterisk, and the tensor product sign. And then S is our 1, 2, 3, 4. 1, 2, 3, 4. All right, so say we wanted to have a surjective function. That means everything in S has to be hit. So there needs to be an arrow going into each one of these. All right, well, these arrows have to come from somewhere. So maybe this 1 comes from the circle, and this 2, maybe it came from the star, and this 3 came from the tensor product. And where's this 4 going to come from? Well, the problem is we know that to be a function, each one of these dots can only have one arrow coming out of it. And this 4 is supposed to go somewhere. If it went to the tensor product, that would have now 2 lines coming out of it. If it went to the star, same thing, or the circle. So the problem here is that when you have a finite set, you can only have as many arrows going out as there are elements in the domain. If there are more elements in the codomain, something is going to have to get missed. Because if you have, so again, like here we have 3 elements in the domain, that means we can only have 3 elements in the range. Remember, the range is the actual outputs. So the most elements in the range we could get would be 3. But if we have more elements than that in the codomain, which we do here, something is going to be missed. Okay, we can think about this as sort of as a reverse version of the pigeonhole principle. All right, so we have a general result we could write down. So if, say, S and T are finite sets, such that the size of S is strictly smaller, smaller than the size of T, then there is no surjective function. No surjective function from S to T. All right, and the proof is simply, we know that the range of this function S has no more than the size of S elements, right? The cardinality of S elements. And if that is less than the cardinality of T, then we know that the codomain is strictly greater in cardinality than the range. And therefore, the function will not be surjective.